Now, so steady state error. This steady state error can be obtained two ways with another classification. How can you obtain steady state error? With error constant methods. Okay, there are two error constant methods. The first one is steady state error constant method. Second one is generalized error constant method. So steady state, or we use the term static. Static or steady state both are same. Therefore, so steady state error constant or static error constants same. Similarly, generalized error constant method, it is also called dynamic error constants. Let us take the first one, steady state error constants. Now, so if you look at the error function E of s is, we have R of s into 1 by 1 plus GH of s. Means my error function depends on what type of input you are connecting, what will be the open loop transfer function GH of s. So let us take inputs one by one and we'll define steady state error constants. There are three error constants: positional error constant, velocity error constant, and acceleration error constant. We will see those error constant and see how to define them. So I will take the first step input. Now the step input is R of s is equal to R by s. R of s is R by s. Now take the error function. Error function E of s is equal to R of s by 1 plus GH of s. So what is the steady state error? Steady state error is ESS is equal to limit s tends to 0 s into E of s, which means limit s tends to 0 s into R of s by 1 plus GH of s. If you take step input, we know what is R of s. That R of s is going to be 1 by s. Now we substitute here, it results. So ESS is equal to limit s tends to 0 s into R of s is R by s divided by 1 plus GH of s. Then we can cancel SS. Then what will be the remaining? Limit s tends to 0 R divided by 1 plus GH of s. Now if you closely observe this equation, your ESS limit s tends to 0 R by 1 plus GH of s. So we want to apply the limit s tends to 0, whereas the numerator R is a constant, there is no s term at all. Okay, so you need not apply this limit to, you cannot apply limit to the constant. Similarly, denominator 1 is there, so 1 is a constant, so we can only apply the limit to GH of s function. So if you do that, I can write ESS is equal to R divided by 1 plus limit s tends to 0 GH of s. Now limit is in the denominator, that to be at the second term. Now the 1 plus in the denominator, we have 1 plus limit s tends to 0 GH of s. This I can define it as one error constant Kp. So how do you write now ESS? ESS is equal to R by 1 plus Kp, where Kp is equal to limit s tends to 0 GH of s. So Kp is called positional error constant. Now we have two conclusions here. One is, what is Kp? Kp is a positional error constant, that is limit s tends to 0 GH of s. And what is the corresponding steady state error? Corresponding steady state error ES is equal to R by 1 plus Kp, where R is the step magnitude. Similarly, we apply the second signal, that is ramp signal. We know what is ramp, the Laplace equivalent. The Laplace equivalent of R of s is equal to R by s square. Then we take the error function E of s. E of s is nothing but we have R of s by 1 plus GH of s. Directly we can write the steady state error equation. ESS is limit s tends to 0 s into R of s by 1 plus GH of s. In place of R of s, we substitute R by s square. Then we can cancel 1 is and 1 is, still one more is there in the denominator. Then it results like ESS is equal to limit s tends to 0 R divided by s into 1 plus GH of s. Then if you multiply s in the denominator, you will get s plus s into GH of s. If you apply the limit to the s, the first s is going to be 0. Then you have ESS is equal to R limit s tends to 0. We are taking the denominator. Therefore, R divided by limit s tends to 0 s into gh of s. So the denominator I can assume one error constant. Therefore ESS is equal to R by kV, where kV is equal to limit s tends to 0 s into gh of s. So this kV is called velocity error constant. So what is the difference between velocity error constant and positional error constant? Positional error constant is limit s tends to 0 gh of s. Here we have kV is equal to limit s tends to 0 s into gh of s. Therefore we have s term. If the position derivative is the velocity. Similarly, we can use parabolic signal. If I give the parabolic, we can write down straight away R of s is equal to R by s cube, and we have ESS, limit s tends to 0, s into R of s by 1 plus gh of s, and R of s is R by s cube. Then if you cancel s and s square is there in the denominator, we can write it as limit s tends to 0 R by s square plus s square into gh of s. Limit s square s tends to 0 is 0. Therefore you will get ESS is R by you have s square into gh of s. Then I can take this limit to the denominator. Therefore ESS is R divided by limit s tends to 0 s square into gh of s. So the denominator term I am assuming another constant. That constant name is acceleration error constant. Therefore we will have ESS is equal to R by Ka, where Ka is equal to limit s tends to 0 s square into gh of s. So these are the three error constants. If you look at all the equation, the summary is like this. So in this summary, the first I will write what is the error constant and what is the corresponding error equation. Positional error Kp is limit s tends to 0 gh of s. Corresponding error is ESS is R by 1 plus Kp. R is the step magnitude. Second is your Kv, velocity error constant, limit s tends to 0. You have s into gh of s, and corresponding error ES is R by Kv, where R is a ramp magnitude. Step magnitude is there, here it is a ramp magnitude. R it can taken as the slope of the ramp. Next, third is acceleration error constant, and we have Ka is equal to limit s tends to 0 s square gh of s, and corresponding error ESS is equal to you have R by Ka. So these are the formulas which are important to calculate steady state error. Now, so we know that the steady state error depends on two factors. One is the input R of s, the other one is open loop transfer function gh of s. Let us take the gh of s. We will see how to calculate these error constants as well as the steady state errors. Now, we can write any transfer function in three different forms. One is polynomial, time constant, and pole zero form. So in this case, I want to write the open loop transfer function gh of s in time constant form. So if you recollect that time constant form, it will be like this. So your gh of s is equal to, in the numerator I have ks into 1 plus s dz1 into 1 plus s dz2 dot 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 divided by, in the denominator we have s power p into 1 plus s into tp1 and 1 plus s into tp2 and so on. So tz1, tz2 and so on are the time constant in the numerator, that is zero related terms, and tp1, tp2 are also time constant, there are the related terms, and s power p, p is the type of the system, means when t is 0, p is 0, it is the type 0 system, when p is 1 it is type 1, p is 2 is type 2 and so on. Therefore s power p, p decides what will be the type of the system. So in steady state error, type plays important role. Based on the type only we will have different steady state errors. Let us take those different types of the systems. Now first I will take type 0 system. So the transfer function will be same, only there is a change in s power p term. In type 0 system, I can take p is equal to 0. When you take p is equal to 0, that is s power 0, that is 1, your open loop transfer function gh of s is equal to, we have ks into 1 plus stz1, 1 plus sz2 divided by 1 plus stp1, 1 plus stp2 and so on. So this is a gh of s. Now we will calculate what is the error constants. So we have the error constants Kp, Kv, Ka. We'll try to find those error constants. First Kp, we know the Kp formula, limit s tends to 0, gh of s. Now gh of s is available, we substitute gh of s here. Then what will be Kp? Kp is equal to limit s tends to 0, so we have a numerator and denominator. So when you substitute s is equal 0, if you observe this time constant form transfer function, you have 1 plus s into tz1. Whenever s is 0, all the terms are going to be 0. In numerator you will get ks into 1. In the denominator again I have 1 plus stp1, 1 plus stp2. So whenever you substitute s tends to 0 or s is equal 0, the denominator will have only 1. So what will be the kv now? Kv is equal to only ks constant. What is ks? Ks is the static gain or DC gain or static sensitivity of the system.